concrete cannot undergo plastic deformation. Steel can undergo plastic deformation. So we will see that how plastic deformation can save us under transient excitation. But remember, under transient excitation, whether the material will fail or not, that is done by comparing stress with yield strength, not fatigue strength. But if it is repeated excitation or periodic excitation, then the stress should be compared by fatigue strength and not yield strength. Remember, this is a fundamental concept of machine design, which is, I don't know. Who is teaching you machine design now? Third year?
Rashmi ma'am, sir.
Okay, okay. That means you all are attending the class. तो ऐसा बताया गया क्या जो मैं बता रहा अभी? That in machine design we have to be very careful whether we should compare the stress with, there are many terms: endurance limit, fatigue strength, yield strength, ultimate strength. Be careful. In machine design there are 4 terms. Stress comes from application, whereas strength comes from material. So when you compare, you should know you should compare with whom. For example, when I'm teaching you people, I should know when I said that you are not doing well, you are not doing enough, I should not compare with MIT student or even IIT student. I should compare you with past batches of VNIT student. So similarly, when you go for a design, you calculate stress. But after you calculate stress, you must know with whom you should compare. So there are 4 terms: endurance limit, fatigue strength, yield strength, ultimate strength. Can anybody explain me how we will select a particular term in machine design? Or can anybody tell me what is the difference between fatigue strength and endurance limit?
So endurance limit is like basically like if a stress cycle is repeated for infinite number of times, the maximum stress that is being repeated, if like basically the maximum value of that repeated stress under which the material will never go failure because of fatigue is endurance limit. But
What is fatigue strength?
fatigue strength is the same thing, but for about 10 to the power 8, 10 to the power 9 cycles.
No, ऐसा नहीं. I mean, you are not 100% correct. Can somebody else will attempt to answer this question? What is the difference between fatigue strength and endurance limit? I'm
Endurance
not
limit
trying.
is
हाँ
defined
बोलो
for
बोलो.
the number of cycles. Fatigue strength is if component is in fatigue, then it how much
बोलो बोलो.
fatigue strength is for infinite number of cycles.
Fatigue
But
strength is
endurance
for
limit
infinite
is
number of
for the
cycles. No. Okay, let me tell you. Whenever we utter the word fatigue strength, we have to remember a material has a particular fatigue strength connected with a given number of cycle. Fatigue strength is not absolute. I cannot say that steel has a fatigue strength of 150 MPa. If I say steel has a fatigue strength of 150 MPa, I should also add the word 150 MPa for number of cycles 10 to the power 4. The thing is that generally as number of cycles increases, fatigue strength decreases. Generally, as number of cycles increases, fatigue strength decreases, not linearly, but if we plot it log graph, it decreases x-axis in a log graph, then we get more or less a straight line behavior. So, but after a certain number of cycles, this drop in fatigue strength gets arrested, means it doesn't drop further. So that value where fatigue strength gets arrested and doesn't fall below it anymore is called endurance limit. So endurance limit is the design for infinite number of cycles, whereas fatigue strength is the design for finite number of cycles. But you have to be very, very careful. Every material does not have endurance limit. Endurance limit is an advantage to the designer. Why it has advantage to the designer? If the designer can prove that whatever stress is happening, it is less than endurance limit, then he can assure the customer that this component can withstand whatever may be number of cycles, 1 lakh or 1 crore or 100 crore. If he can show that the stress is less than endurance limit, he can assure the customer that don't worry, you can use it lifetime. Unfortunately, steel has endurance limit, aluminum doesn't have. Most of the material, they don't have endurance limit, let me tell you. Actually, in mechanical engineering, I personally believe that there should be another subject on materials. Your knowledge of materials is insufficient. And when I say knowledge of materials, it is not microstructure details. General information of materials you must have. Because today materials have become versatile. So if our material has endurance limit, as a designer, I will try to keep the stress below the endurance limit. But suppose it doesn't have an endurance limit, then how do I do the design? I cannot design a lifelong safe design. So what will be my sentence? That this is the stress which will cause a failure, but not before 10 to the power 4 cycles. Not before 10 to the power 5 cycles. So these are called finite life design. So, machine design is not what you are learning in your class. Machine design is much more. A design cannot be absolute design. What is meant by absolute design? Absolute design means it will never fail. That is absolute design. No. Today we have accepted finite life design. And there is another concept of design, we call it design to fail. Means where we design such that it will fail. This is very interesting. We design such that a failure will take place. An example I'll give you. In MiG aircraft, there is an automatic pilot ejection system. So if the pilot thinks that his aircraft has gone out of control and it is going to crash land quickly, he should get separated from the aircraft. अब उसमें बैठा रहेगा तो वही होगा जैसे आप लोगों का हाल है. In online you all are thinking कि अरे बड़े मजा है, घर में बैठे हैं. You don't know that in another 1 year you are going to crash land. जब इंटरव्यू में बैठोगे तो पता चलेगा. So in MiG aircraft, when the pilot knows that his aircraft has gone out of control, it is going to crash land somewhere, he has to separate out from the aircraft. So there is automatic ejection system. सीट जो अभी तक प्लेन के साथ बांधा हुआ है वहां पे फेल्योर होता है. दैट फेल्योर इज इंड्यूस्ड फेल्योर. फिर सीट प्लेन के बाहर आ जाता, ऑफ कोर्स विथ पैरासूट एंड ऑल, एंड द पायलट गेट सेपरेटेड फ्रॉम द एयरक्राफ्ट. सो दिस इज ए डिजाइन बाय फेल्योर. कभी कभी हम फेल्योर को भी डिजाइन करते हैं. ओके इसका दूसरा नाम है फेल सेफ डिजाइन. फेल सेफ डिजाइन. फॉर एग्जाम्पल, यू मे नॉट नो the coupling between the bogies of a train. Nowadays, they are being designed so that through the coupling, the engine can pull all the bogies. But suppose now engine and some of the bogies are trying to topple because of derailment, तो coupling टूट जाएगा. Coupling टूटने से क्या होगा? पीछे का जो बॉगी है वो derailment नहीं होगा. So nowadays, the couplings are also getting designed. पहले क्या था? इतना मजबूत कपलिंग हम बनाते थे कि अब वो इंजन गिरा, डिरेलमेंट हुआ तो वो लेके सारे बॉगी को लेके डिरेलमेंट होगा. But nowadays it's not happening, if you see. So this is called fail safe design. Means we design where we allow it to fail. But anyway, that is not my, I think I am getting out of vibration and teaching you some other subject. ऐसे वाइब्रेशन इतना बड़ा सब्जेक्ट है जिसमें मुझे 4 सेमेस्टर लगना चाहिए. I cannot complete in 1 semester. But why I am discussing other things also? Because they are very much connected with vibration. Ultimately, what is vibration? Vibration, why you should study vibration? So that you can understand failure properly, and wherever needed, you can avoid failure. So vibration is a part of machine design. It is actually ultimate machine design. Whatever you learn in machine design, that is not the complete machine design. That is just the half of machine design. You have to also study vibration, because nowadays 99% of failures are happening because of vibration. They are not happening because of your machine design failure. Machine design has reached final expertise. But even if you design a component using your machine design knowledge, still failure can take place. That is because of vibration. Of course, another important subject, can anybody name that? These two subjects together are causing failure in last 40-50 years. One is vibration, any other, there is another subject one must study. अरे कम से कम सब्जेक्ट का नाम तो पता होना चाहिए.
मेटलर्जी.
हाँ,
मेटलर्जी.
अरे नहीं, मैकेनिकल इंजीनियरिंग का सब्जेक्ट है वो. Okay, I will not waste time. Fracture mechanics. Fine. So these two subjects, so to prevent failure, last 50 years, ये दोनों सब्जेक्ट का इंपॉर्टेंस काफी बढ़ गया है. Anyway, so let me go back to vibration, but before that, fatigue strength is finite life design. Can anybody give me one example where we go for finite life design? A very, very common example. You know, aircraft. Aircraft के जो body है, what is the name? Fuselage. Aircraft का जो body है, it is called fuselage. Now, this aircraft, does it undergo fatigue loading? क्या लगता है? I mean, in the interview, suppose you are asked, do you think aircraft body is a pressure vessel? What will be your answer?
Yes, sir.
Why?
Sir, actually, it is internally pressurized, and when it goes in air, due to variation in lift, there is fatigue on the fuselage of the body and the wings.
तुम इतना लंबा कहानी मत बोलो. When it is in the airport, inside pressure and outside pressure, they are same. नहीं तो हम दरवाजा कैसे खोलेंगे? But when it goes in air, outside pressure decreases. You know that with altitude pressure decreases, that all of you know. But inside pressure does not decrease. It remains, we call it cabin pressure, same as it was in the airport. So now inside pressure is larger, outside pressure is small, so it becomes a pressure vessel. Now again when it comes back and does the landing, फिर से दोनों pressure same हो जाता है. So this is called cyclic load. Every time an aircraft goes up, one cycle of pressurization takes place. Fine. So if I have to design the aircraft body, I have to design against fatigue. But should I design against infinite number of, now aircraft body is not steel, remember. So I will not demand an endurance limit there. I will say 1,000 flight, 2,000 flight. So there is a design life of an aircraft. We calculate how many number of flights it is required in that design life, maybe 10 years, maybe 15 years. And we design for that number of cycles. So aircraft is an example where we go for finite life design. So we need fatigue strength. We don't need endurance limit. So 4 things I have introduced: ultimate strength. So now let me ask you another question. Ultimate strength and yield strength, they classify material into 2 groups. What are the names of these 2 groups? Jaldi se. Brittle material, ductile material. In brittle material, failure occurs right after the yield strength. In ductile material, complete failure occurs after the ultimate strength. So for ductile material, there is a buffer between ultimate strength and yield strength. In between, there will be functional failure, but there will not be material failure. Okay? So let me come back to this slide. काफी दूसरे चीज का चर्चा हो गया. But anyway, so what does it mean? It means that for periodic loading, I need fatigue design, but infinite number of cycles. Remember, infinite number of cycles. If it is vibration induced, aircraft fatigue is not vibration induced, that is depressurization and pressurization. If it is vibration induced and the force is harmonic or steady state or periodic, my design concept will be fatigue design under endurance limit. If the material does not have an endurance limit, I have to be careful. Means I have to accept that this material cannot last long. तो फिर मैं उसके ऊपर मुझे बताना पड़ेगा that this material can only last or withstand so many cycles, 10 to the power 5 cycles or 10 to the power 6 cycles. वो लिखना जरूरी है if the material does not have endurance limit. Anyway, but for transient excitation, endurance limit or fatigue strength has no meaning because the maximum amplitude doesn't repeat it again and again. It comes only once. So here I have to go by tensile strength, and sometimes I have to take the advantage of ultimate strength also. Okay? So with this introduction, let me begin the mathematics. इतना इंट्रोडक्शन जरूरी था क्योंकि आने वाला मैथमेटिक्स भयंकर है. चलो, ये क्या चीज है? सो आई एम शोइंग यू, दिस इज कॉल्ड हाफ साइन वेव एक्साइटेशन. इसको ड्रॉ करो, अपना खाता में ड्रॉ करो. दिस इज कॉल्ड हाफ साइन वेव एक्साइटेशन. This is force. I mean, don't take it as the bump. Bump also looks like this, but that is not, y-axis is not force, that is support excitation. But right now my picture is force excitation, where the force varies as per a sine curve, but it's not a complete sine curve. It lasts only for half time period. The force lasts for half time period. So T0 is what? T0 is T by 2, capital T by 2, where capital T is the time period of sine wave. Capital T is the time period of sine wave. And this is half time period. Fine. So if this is the excitation, we want to study how a single degree of freedom system will vibrate. Now this is a tangent excitation because it lasted for between 0 to T0. Uske baad excitation vanished. Now we want to study what will happen to a spring mass damper system. So how do we do it? Okay, before we study that, few more transient excitation. This is called unit step excitation. Excitation suddenly increases to a value, not unit, step excitation. Excitation suddenly increases to a value, but then it remains at that value for infinite time. This is pulse excitation. Excitation suddenly goes up, remains at that value for a period. This is called period of the pulse, and then again vanish. This is pulse excitation. This is triangular pulse. Then this is ramp and step. So transient excitation can have different looks. It can be half sine wave, it can be step, it can be pulse, triangular, ramp and step, and many more combination transient excitation can have. So to study the behavior, let us pick up half sine wave. But before that, let's look at this excitation also. Now this is under earthquake. Under earthquake, the excitation never looks like all previous excitation. They have some geometric representation, matlab straight line. But here I cannot represent the values by any straight line. It is random. So this is called random excitation. So random excitation is a part of transient excitation. This excitation is transient, but they are not random. They are not random. Whereas this excitation is not only transient, it is random. Now, why I'm calling transient? Because it lasts for 20-30 seconds and after that it vanishes. So it is not only transient, it is a random excitation. So this kind of excitations are even more difficult to mathematically handle, but we will do everything. Fine. So after I have introduced different types of tangent excitation, let me come to directly the mathematics of, चलो इसका मैथमेटिक्स चालू करते हैं. तो देखो अभी लिखो, जो भी लिखा हुआ है वो लिखो, लेकिन समझ के लिखो. What we are trying to do? ये इक्वेशन हमें क्या बताता है? That we have a spring mass damper system where we have an excitation that looks like this. So the excitation exists between a time 0 to T0, and beyond that time excitation becomes 0. So this is called forced phase and this is called unforced phase or free vibration phase. This is called forced vibration phase up to T0, forced vibration phase. Beyond T0 it is free vibration phase. दोनों का रेस्पॉन्स अलग अलग होगा. सो फर्स्ट वी फाइंड आउट फोर्स्ड वाइब्रेशन रेट. ठीक है, कैसे निकलते हैं? तो इनिशियली हम डैम्पिंग नहीं पकड़ रहे, सो वी आर नेग्लेक्टिंग डैम्पिंग because with damping my calculation will be little more complicated. So initially we are neglecting damping. So if we neglect damping during the force phase, this will be the solution. क्योंकि remember complementary solution comes in picture. Why? I have neglected damping. And not only that, in transient excitation, complementary solution for damping also is to be considered. Because in transient excitation, I am not looking at the response in steady state, because steady state will not occur at all. So if damping is there, then also I have to include the complementary solution. ठीक है, तो फिलहाल हम damping को consider नहीं कर रहे to keep the mathematics simple. So if we neglect damping, then this is my solution as long as the force exists. Then what do? I calculate the displacement at this point. I calculate the velocity at this point, and that becomes the initial condition for vibration T0 onward. So after T greater than T0, it is a free vibration. But that free vibration has started with the initial condition. So time frame को मुझे shift करना होगा. Free vibration का solution क्या है? T minus T0. Because free vibration का time period origin is here. So this represents free vibration solution. This represents free vibration solution. This solution exists for T greater than T0. And this solution exists for T less than T0. समझने का कोशिश करो. इसको लिखो and try to understand whatever I have said. I think it is difficult, but इसको लिखो और try to understand. If anyone has any doubt, you can ask me now, because now onward our mathematics will be more difficult. अगर कहीं पे समझ में नहीं आ रहा तो पूछो. I think you have understood. So what do we do now? What do we do now? We have got the vibration during post vibration phase. We also have the vibration during free vibration phase. अभी हम क्या करेंगे? इसकी मैक्सिमम वैल्यू निकालेंगे और इसकी मैक्सिमम वैल्यू निकालेंगे. दोनों में जो ज्यादा होगा that will be the maximum vibration displacement under this transient excitation. So phase 1 we will find out maximum, phase 2 we will find out maximum. We will compare. Whosoever is greater, we will take that value as the maximum vibration displacement because of this half sine wave excitation. So to find out the maximum value, we need lot of mathematics. Okay, हमें differentiate करना होगा. So I have explained that mathematics here. You just go through. You just go through that how do we find that maximum vibration displacement. Okay, but थोड़ा सा mathematics गंभीर है. So I will give you the PPT. घर में बैठ के पढ़ना पड़ेगा. Fine. But let me come to the figure. This figure tells me at a particular omega n by omega, Now this omega is pulse frequency. This omega does not mean that my excitation is harmonic. My excitation has half sine wave, but that half sine wave corresponds to a frequency. Okay, how do I calculate that frequency? T0 is capital T by 2. So capital T is 2 into T0. And capital T is 1 cycle. So that is 2 pi by omega. So 2 pi by omega is equal to 2 into T0. Therefore, omega is equal to pi by T0. You can write down this derivation. Sorry, I don't have it on PPT. This pulse frequency omega finally comes out to be pi divided by half sine wave duration T0. You can derive it. Now this T0, I can change. I can make it 1 second. I can make it 2 seconds. Accordingly, my omega will change. So omega changes as the pulse duration changes. Omega n changes as the value of m and k changes. So both can change. So I take a ratio and I plot maximum response against this ratio. I get this graph. Fine, I get this graph. Now this graph tells me if I am using half sine wave excitation in a particular application, I will calculate omega. Omega कहाँ से आएगा? Pulse duration से. I'll calculate omega n. कहाँ से आएगा? Under root k by m. I'll find out the ratio. Suppose the ratio comes out to be 1. Then along 1, whatever is the maximum value, I will say this is the maximum vibration that will occur. And then I will calculate the stress. And that stress I will compare with yield strength. Fine. So if you look at the graph, you will see as a designer, this zone I have to avoid. That is omega n by omega, not exactly 1. It is slightly more than 1. I think it comes around 1.4 or 1.57. So this zone I have to avoid because in this zone, my vibration that occurs only once, but the maximum value is really very, very large. So I should try to avoid. इसको कैसे avoid कर सकते हैं हम? We have no control on omega. So it is better if I work in this zone. That means low omega n zone. Low omega n करेंगे तो मुझे stiffness को घटाना पड़ेगा. ठीक है? I have to reduce the stiffness. So as a designer now, I manipulate stiffness or mass so that the ratio is in this zone. I should try to avoid this zone. So this is today's discussion. Tomorrow we'll again come back to this graph. But up to this graph, whatever mathematics and whatever I am giving, please study it today because now onward mathematics will be difficult. You cannot run away. ठीक है? चलो आज का क्लास हो गया. इतना दूर का पीपीटी मैं भेज दे रहा. Fine. चलो you can leave.